5, we're going to be revisiting the topic of isomers and putting a little bit more context into it. In this first part, we're going to be talking about the chirality of molecules. So we're going to be looking once again at configurational isomers. Remember, these are the ones that have the same connectivity, but they have a different 3D arrangement other than the rotation around the single bond. Remember, conformers were our ones that just rotated around the single bond, and that's what we looked at in chapter 4. So with configurational isomers, we have a couple different types that you want to be familiar with. The first one is going to be in an enantiomer. And enantiomers are non-superimposable mirror images of each other. We're also going to talk about diastereomers. Diastereomers are stereoisomers that are not going to be mirror images. So to look at the context of enantiomers and looking at the context of mirror images, I want to look at 2-chlorobutane. So first I just want to look at butane, and we're going to focus in on carbon atom number 2, and we're going to focus in on the tetrahedral nature of carbon atom number 2. So in this structure I have it drawn so that we see one of those hydrogens is pointing back. I have it labeled as HB. One of those hydrogens is pointing forward, and I have it labeled as HA. So what we're going to see is we're going to compare the two compounds for 2-chlorobutane of when chlorine takes HA's position or when the chlorine takes the HB position, and we're going to compare the two structures. So the first one I'm going to draw is replacing the HA with the chlorine atom. So you'll notice now that the chlorine atom is pointing out in front of the plane. We can do the same thing, but this time we're going to replace the HB with the chlorine. And now you'll notice that the chlorine atom is pointing back in our structure. So when we look at these two structures, this is what they look like in our screen. I have the structure over here on the left-hand side where the chlorine atom is pointing forward. I then have the structure on the left-hand side, or the right-hand side, where the chlorine is pointing back behind the screen. So we have these two structures and we want to compare them. So I'm just going to quickly redraw the structure where we have replaced the HA. And in this structure, we're going to once again keep in mind that our Cl is pointing out at us and the hydrogen is going back behind the plane of the screen. So now what I'm going to do is I am going to draw the mirror image of this structure. So what we want to think about is we want to think about a mirror being in between the two structures. And remember, in a mirror image, everything appears reversed. So when I get ready to draw my mirror image, that is what the chain would look like. So notice it's the exact reversal of what we have. And then the mirror image of this, chlorine is pointing out, but it is on the other side, and our hydrogen is pointing back. So this becomes the mirror image of our structure. And what I want you to notice about the mirror image of this structure is it is a 180-degree rotation of the molecule that we drew with the replacement of the Cl in the back of HB. So if we look at this with our structures, again, here is the structure that I originally drew. I've got my CH3 going down to my CH3, and I've got my chlorine atom pointing out in front. When I drew the mirror image of it, it looks like that. I've got it exactly opposite, so it's mirrored. The chlorine is pointing out in front of you, but it's on the opposite side of the structure. These are my mirror images. So all I have done is I have rotated this 180 degrees, and it matches that structure that we have on the right with the chlorine pointing backwards. So that is how we look at drawing our mirror images. But what you'll want to notice is this mirror image that we made is non-superimposable. Non-superimposable means if I put them on top of each other, they match, would be imposable. Non-superimposed means they don't match. So if you'll notice, when I try to put them on top of each other, they don't match because the chlorine atoms are pointing in different directions. So this mirror image that we drew is non-superimposable, which means that these are going to be enantiomers for us. because that is what an enantiomer defines. it matters. It is different if the chlorine originally is pointing back or if the chlorine is originally pointing forward. Those two positions are different for us in terms of the spatial arrangement. So we call these non-superimposable mirror images enantiomers. If you think about it, no matter how I rotate this structure, so if I rotate the structure around those single bonds, you'll notice that that doesn't impact, because then as still as I start to line up my carbon chains, no matter what I do, no matter how I rotate them, those two chlorine atoms are on opposite sides of the chain itself. So these are our enantiomers. They are configurational isomers. They are different in their three-dimensional space. No matter how we rotate around single bonds, they are different. These enantiomers here are non-superimposable mirror images because when we draw the mirror image, they are mirror images of each other, but they are going to be non-superimposable for us. When we look at this, every molecule has a mirror image, so we can do that context of drawing a mirror image regardless of the molecule itself. So if I just draw a simple tetrahedral carbon atom, it's got one chlorine on it, it's pointing out at you, it's got 3 hydrogens on it. I can again draw the mirror image of this structure because we can draw a mirror image for everything. But what we're going to see is that not all mirror images are going to be enantiomers, because here's my mirror image. But if I take this mirror image and I rotate it 109.5 degrees, I get to the exact same structure that we started with. So these are what we would call imposable mirror images. So these would not be enantiomers. Because they are going to be superimposable. So if we look at the structure that I just drew, here's my chlorine pointing out, my hydrogen's in the plane, my other hydrogen. When I get ready to draw the mirror image of it, here's what my mirror image would look like. So we've got the carbon atom pointing out. It's directly opposite. But if I just rotate this 109.5 degrees, you'll notice that they're identical. If I overlap them, all the bonds are pointing in the same direction. They're completely superimposable. So even though we have a mirror image, because every molecule we can draw a mirror image for, not all of those mirror images are what we're going to classify as enantiomers. So you need to make sure that when you draw the mirror image, you rotate it as many ways as you possibly can before you determine if you have an enantiomer. Because if you can rotate that mirror image and make it be superimposable on the first structure, it is no longer considered an enantiomer because it is superimposable. And remember, enantiomers cannot be superimposable. They're those non-superimposable mirror images. The reason we want to know about these enantiomers is because enantiomers are going to play a role in reactivity as well as some physical properties that we'll be discussing towards the end of this chapter. So one of the other terms that we're going to use with this is this term of chirality, because a chiral molecule is a molecule that cannot be superimposed on its mirror image. So it's kind of a more broad term than what an enantiomer is. And an enantiomer is a non-superimposable mirror image. So molecules that have this chirality associated with them are going to have non-superimposable mirror images with them. We can also define a molecule as being achiral. So please kind of notice the terminology. We have chiral molecules and we have achiral molecules. Achiral molecules are going to be molecules that have superimposable mirror images. So they will not have enantiomers associated with them. So this is kind of that broad terminology that we will be using to define a molecule itself. Is it a chiral molecule having a non-superimposable mirror image? Or will it be an achiral molecule that does have a superimposable mirror image? So some of the things we're going to look for testing for chirality, because one of the things we want to be able to do is look at a molecule and state whether or not it is a chiral molecule. So one of the tests we're going to do is if a molecule can rapidly convert between conformational isomers, it is usually going to be achiral, meaning it has a superimposable mirror image. So what we mean by this is you have to make sure that you account for rotation around single bonds. Remember, we just had our conversation in the last chapter about how we're constantly rotating around those single bonds. So we have to make sure that we watch for that rotation when we're doing our comparison for our molecules. So I do want to look at an example of a 4-carbon chain. I'm going to put a bromine on carbon atom 2. I'm going to put a bromine on carbon atom number 3. And notice now I'm going to start imposing some directionality. So instead of drawing everything nice and planar like we have been so far, we're going to start putting that tetrahedral nature around those carbon atoms. So the bromine on carbon atom number 2 I have pointing back behind the plane. The bromine on carbon atom number 3 I have pointing out in front of the plane. So starting to look at the three-dimensionality that we have with our structures. I'm now going to draw the mirror image of this structure. So this is what our mirror image would look like. But what we have to remember is that we have freedom of rotation around that single bond. So if I just do a rotation around carbon atom 2 to carbon atom number 3, which remember we can do since it is a single bond, I can actually get to the original structure that we have. So even though we see some three-dimensionality associated with our structure, like we saw with those 2-chlorobutane, we see that same three-dimensionality here with the bromines pointing out, the bromines pointing back. Because of the rotation around that single bond, I have an achiral molecule. Its mirror image is going to be superimposable on the first one because of that freedom of rotation that we have. Another example that we can look at is going to be in a ring structure. So if I look at this ring structure, I'm going to put some halogens on it once again, and again I'm going to give some directionality like we have seen with our rings in terms of the faces. So some of our attachments are going to be on one face, some of our attachments will be on the other face. So once again we see that tetrahedral nature on those carbon atoms. Once again, I want to look at the mirror image because we have to be able to decide if that mirror image is going to be superimposable or not. So I'm going to draw the mirror image. Let's make that a BR. So there's my mirror image of my structure. And what we're going to see is we do want to look at rotating this. So I'm going to flip it over and I'm going to rotate. And when I flip this molecule over and I rotate it 180 degrees, I get the exact same structure as my first one. So once again, this structure would be considered a chiral because of those rotations that we have. You could look at this in the chair structure as well because of the chair flip that we could do with this. We would see the same type of achiral structure or achiral nature associated with this molecule. So if you are having trouble rotating these things in your brain, looking at them on paper, seeing that flipping, seeing that rotating, I encourage you to come up with some model kits. You can either purchase a model kit, there are a ton of them out there, or you can actually figure out how to do this with pencils. I've seen some creativity when it comes to pencils or straws or things along those nature, so that you can kind of get that visual hands-on representation if you are struggling with seeing these rotations and flipping on the screen itself. So one of the things that can help us with rings is going back to those Haworth projections. So remember the Haworth projection put the ring in a flat nature, and then it showed us the two faces that we have on our ring. Sometimes these projections can make it a little bit easier to denote whether or not something is going to be chiral or achiral. So if we go back to the structure that we just looked at, but put it into the context of the Haworth projection, this is what it would look like. I had a chlorine and a bromine on the top face. I had a chlorine and a bromine on the bottom face. So then when I get ready to look at the mirror image of this structure, sometimes this is a little bit easier to see the flipping because we don't have to flip it quite as much. All you'll notice is if we just do a quick 180-degree flip of our Haworth projection, you will see then that it hopefully matches our original structure directly. So again, it's going to be a nice achiral structure. So sometimes these projections can help a little bit in terms of predicting the achirality if you were struggling with looking at it flat, and the dashed and the wedges as well. So just to look at one more example, because not all rings necessarily will be achiral, just like all straight chains are not necessarily always achiral. So here's another 6-membered ring. We've got a chlorine on top, we've got a chlorine on the bottom. If I draw my mirror image, and now if you try to rotate this, you try to flip this, it will never match. So this is actually a chiral ring structure that we have. No matter how I flip it, if I flip it 180 degrees, the bromine and the chlorine are in the back of this structure. If I try to then rotate that structure around, the chlorine and the bromine are on opposite sides that they need to be. So no matter how I rotate or flip this structure, the mirror image is considered non-superimposable. So it is going to be a chiral molecule for us. So this is one of the things that you can think about that we have to look for when looking for chirality. We have to watch for rotations around single bonds, and we also have to make sure that we flip and rotate our rings to make sure those mirror images are superimposable or non-superimposable. The second thing we're going to look for is going to be a plane of symmetry within the molecule. This is basically where half the molecule is a mirror image of the other half. If our molecule possesses that plane of symmetry, it is usually going to be achiral. So if you go back and you look at that one ring structure that we drew, or if you look back at the 4-carbon chain with the 2 bromines, if you draw a line down the middle and split the molecule in half, you will notice that those had planes of symmetry in them, that they had half the molecule mirrored the other half of the molecule. And when you see that, you can pretty much assume that the molecule is going to be achiral, that the mirror image of the entire molecule we will be able to rotate, and it will be superimposable on the original structure. So sometimes looking for that plane of symmetry will clue you in that you have an achiral molecule, a molecule that has a superimposable mirror image. The next thing that we're going to look for chirality is we have to look for what we're going to call a chiral atom, or a stereocenter. If the molecule does not have a stereocenter, it cannot be chiral. So a stereocenter is going to be any tetrahedral atom that has 4 different attachments. Usually if we have at least one of those in the molecule, oftentimes we're going to have a chiral molecule associated with it. So what we're going to be looking at with this is we are going to be finding those stereocenters. So oftentimes before you test the entire molecule for chirality, you want to zoom in on all the tetrahedral atoms that are sp3 hybridized, and you want to decide if they are a stereocenter or not. So just to kind of look at a couple of examples, if I have a carbon that has 2 hydrogens on it and 2 chlorines on it, this is always going to be achiral. It does not have a stereocenter. It's got 2 of the same attachments. So if I draw the mirror image, I will be able to rotate it and make it look exactly like the first. If we take out one of those chlorines and we make it a bromine, so if we look at something along this structure, this is still going to be considered achiral because it has 2 hydrogens on it. So it's not going to be a stereocenter. If we draw the mirror image and we rotate it, we will be able to make it superimposable on the original molecule that we drew. So let's look at one more example. Let's keep a bromine and a chlorine on there, but this time let's put a methyl group on there in place of one of the hydrogens. So now you'll notice that this carbon atom has 4 different attachments on it. Those 4 different attachments are going to make it chiral. It is a chiral center, so it will make this structure chiral. If I draw the mirror image, it will have a non-superimposable mirror image. If we interchange any of those, so if I switch the CH3 and the Cl in terms of their directionality, the CH3 pointing back, the Cl pointing forward, it will be a different 3-dimensional structure that we cannot rotate to make look like this first one. So that's what we're looking at in terms of looking for these stereocenters. If a molecule has at least one stereocenter, it is usually going to be chiral for us. One of the exceptions to the stereocenters and just looking for a stereocenter alone is what we're going to call a mesocompound. Mesocompounds contain at least 2 stereocenters but it has a plane of symmetry to make it achiral. So if you think back to those first couple structures that we drew, with the 4-carbon chain and the 2 bromines, it had stereocenters on it. Each one of those carbon atoms had 4 different attachments, carbon atom number 2 and carbon atom number 3. But when we looked at it, it was achiral because it had that plane of symmetry, that when we drew the mirror image was superimposable due to rotations and due to that plane of symmetry. So these are what we refer to as mesocompounds. They contain stereocenters. They can contain chiral centers, stereocenters, but the molecule as a whole is achiral because it has a plane of symmetry or because it freedom of rotation around bonds. So these are going to be achiral structures. Just to give you another example of a mesocompound, if I look at a ring and I'm going to put 2 bromines on that ring, both of those bromines are going to be pointing out. You'll notice that this structure has 2 stereocenters. Each one of the carbon atoms that is attached to the bromine is considered a stereocenter. One carbon atom has a bromine attached to it. It has a hydrogen attached to it. It has the carbon chain, so it has a CH2 going up CH2. It then also has a CHBr if we go down, and those are 4 different attachments on that carbon atom. So that is considered a stereocenter. If we look at the carbon atom down at the bottom that I also have marked with an asterisk, it is a chiral center for the same reason, 4 different attachments. We will oftentimes denote chiral centers by putting that little asterisk beside the carbon to denote this is a chiral center. But if we look at the mirror image and we do a rotation, it is an achiral molecule. So this is what we refer to as a mesocompound. It contains stereocenters, it contains 2 of them, but it is overall achiral because of the plane of symmetry associated with this structure. Any of our sp3 hybridized atoms can be considered chiral, not just looking at carbon atoms that are sp3 hybridized, but any of our atoms that are sp3 hybridized and have those different attachments can be considered chiral. So if we look at nitrogen, and if nitrogen has 4 different attachments associated with it, it will be considered chiral for us. It will have a non-superimposable mirror image, but it does have to have 4 different attachments in order for it to be considered chiral. What we do have to watch for is that it has to actually be bonding attachments. So if I make this nitrogen have a 0 formal charge and have the lone pair on it, this now only has 3 attachments. It does have 4 different electron domains because of the lone pair, but that lone pair isn't an attachment. It's not a bonding electron domain. So this is not a stereocenter, and it's not going to be considered chiral or achiral because of the lone pair not being an attachment. What we actually see is in this structure, it rapidly interconverts. Since that isn't a bond, it rapidly converts from what we would call one form to the other form in terms of the directionality or the 3-dimensional space, because that lone pair is not a true bond. So really what happens if we look at this in terms of another diagram of an interconversion that we're going to be looking at. So there's my trigonal pyramidal nitrogen with that lone pair on it. It is going to rapidly interconvert into the other form, what we would have as the mirror image of it. It actually flips into this. It's not a true different structure or different molecule. It's kind of what we refer to as a pseudo-rotation, this rapid flip that we have, kind of like we saw that ring flip as a pseudo-rotation. Anything with a lone pair will rapidly flip as well. It flips through a structure that takes advantage of the unhybridized p orbital. So since those aren't, it isn't a true bond, so they're my lone pair of electrons in an unhybridized p orbital, and it really goes through that trigonal planar shape that we would see where we've got one of the unhybridized p orbitals, the other 2 are going to be, or the other 3 bonds are going to be sp2 hybridized instead of sp3 hybridized. And we can do this rapid interconversion because those lone pairs aren't bonding. So they're not stuck in that hybrid orbital because there's no overlap. So it can rapidly interconvert between the two mirror images, which doesn't mean we have to do any rotation to make it match the original structure. It literally just has to flip back and forth, do a pseudo rotation. So when we're talking about 4 different attachments to sp3 hybridized carbon atoms, in order to be considered chiral, they have to be attachments. They have to be bonding electron domains. It will not work if we have these non-bonding electron domains. So let's talk about some of the other types of stereoisomers other than just those enantiomers, those non-superposable mirror images, because we also have diastereomers. Diastereomers are going to be our stereoisomers, so 3 different 3-dimensional space, but they're not going to be mirror images. What we're going to see is as the number of stereocenters increases, so does the number of potential stereoisomers that we have within our structure. So the formula that we use to determine the total number of stereoisomers is 2 to the n, where n represents the number of chiral centers that we have within our structure. So we can have a lot of stereoisomers, but not all of them are going to be enantiomers, the mirror image that we have, that non-superimposable mirror images. So we also have diastereomers, which are stereoisomers that are not going to be mirror images, but they're still going to be stereoisomers. We also will use the term of an epimer. An epimer is going to be any 2 diastereomers that differ only at one chiral center. The rest of them all stay the same. So if we look at them in terms of directionality, if we've got 2 of them, one of them will stay the same between the 2 structures. The other one is going to be different. So 2 epimers are 2 diastereomers that differ at one chiral center, and the rest of those chiral centers all stayed the same in terms of their directionality. One of the new drawings that we're going to learn for this chapter are going to be Fisher projections. Fisher projections will oftentimes help us identify those stereocenters and the directionality associated with them. So with Fisher projections, we're going to view everything as being in a plane, and we're going to basically form these big T's and plus signs as we go down. So we'll have a top area, we'll have a bottom area, and then we can compare what is on the left and what is on the right for our chiral center. Even though we are viewing them in a straight plane, they're not really in a straight plane. For Fisher projectors, what we are assuming is we've got that center carbon atom, which is the middle of that plus sign. Everything that is perpendicular is considered to go back. So the W and the Y are back behind that carbon atom. When we look at the Z and the X that I have there, they are coming out of the plane. So nothing is left in the plane in reality for a Fisher projection. For a Fisher projection, we have rotated so that everything is either pointing out or going back. So here's what my structure would look like. Everything that is perpendicular to the floor is pointing back. Everything that is parallel to the floor is pointing out at you. So it's just looking at it in a different rotation. But when we actually look at the Fisher projection, which is the one that I drew first, that's the true Fisher projection, we can very easily see what is on the left and what is on the right. And this will help us to determine enantiomers or mirror images, or if I have a diastereomer. So looking at an example of a Fisher projection and what it allows us to do, I'm going to take a nice 1, 2, 3, 4 carbon chain, and I'm going to look at carbon atoms 2 and 3 because those are going to be my chiral centers. So you'll notice that each one of those carbon atom 2 and carbon atom 3 are both considered chiral centers for us, and they have 4 different attachments associated with them. So I'm going to draw the mirror image of this in our Fisher projection. So for my mirror image, this would be a non-superimposable mirror image. So you will see here that no matter how I rotate it, no matter how I flip it, I will never get the bromines and the chlorines back on the same side in the same directionality. So these 2 things would be enantiomers for us. They're non-superimposable mirror images. But since I have 2 chiral centers, remember I should have more stereoisomers. 2 to the 2 is equal to 4. So I should have 4 stereoisomers that I can draw. So let's now, instead of drawing the complete mirror image, let's only change one of the stereocenters. So I'll leave the first stereocenter that I drew the same, but I'm going to flip only my second stereocenter. So I'm just going to reverse the side that the carbon and the chlorine are on. This is now what we're going to refer to as a diastereomer. So these would be diastereomers of each other when we actually look at the difference between them. They have two chiral centers. One has stayed the same, one of them has changed, and that's how we define our diastereomer. I can then take this diastereomer and I can actually draw the mirror image of that as well. So these two structures here would now be back to being my enantiomers. They are non-superimposable mirror images that we have, but again, they would be diastereomers of the first one, where we have changed one stereocenter, but we have left the other one the same. So then they would be diastereomers from what I originally drew as well. And there are my four stereocenters that I can draw since I had two, or stereoisomers that I can draw since I had two stereocenters in my structure.